All right, let's look at some ways to determine the structures of organic molecules. So historically, to test for functional groups within molecules, we do chemical reactions. So we could take a small sample of the molecule that we don't know the structure of it, and we would add things to it that we know what the outcome would be if we had particular functional groups. So for example, if we had an alkene, we could add bromine to it, and if it decolorized bromine, that would be an indication there's an alkene because it reacts with bromine to give a colorless dibromoalkane. Or if we had an alcohol, we could treat that alcohol with concentrated sulfuric acid. The alcohol would be normally soluble in water, but then when we add concentrated sulfuric acid to it, it would dehydrate to give an alkene that is insoluble in water, and so we would see a phase separate out. There's lots of these chemical tests for functional groups. However, they really don't give us that much information. They give us some information about functional groups, but they don't tell us the exact structure of the molecule. And I guess historically, chemists did degradation experiments. So they would take that molecule and they do chemical experiments to convert it into other molecules they know the structure of, and they use inference to work out what the structure of the molecule is. These days we have very powerful, sophisticated instruments to work out the structure of an organic molecule. And we're going to talk about the first of those in this video. Now, related to this, the first technique I'm going to talk about is mass spectrometry. And that's really about trying to work out the molecular mass and the molecular formula for the compound of interest. And to do that, we want to work with something called the Index of Hydrogen Deficiency. So this is the sum of the number of rings and the number of pi bonds in a molecule. And it relates to what we would expect for a non-cyclic, completely saturated hydrocarbon or molecule that's related to our molecule of interest. So the index of hydrogen deficiency, for example, with a hydrocarbon, we could work it out. The reference would be CnH2n plus 2. So we know that that is the general formula for an acyclic hydrocarbon. And we can work out what does our molecular formula, how does it correspond to that reference number for a hydrocarbon? Because every time we, for example, have an acyclic molecule, if we want to join together the ends of an acyclic hydrocarbon, we would need to lose two hydrogens to join those two ends up. And likewise, if we wanted to make a pi bond, we would need to lose two hydrogens within the molecule to make a new pi bond. And so we can tell from the molecular formula something about the number of pi bonds and the number of rings. So here's an example of doing that with cumene, which has molecular formula of C9H12. So for a hydrocarbon, we would expect an acyclic hydrocarbon to be a reference formula of C9. H2n plus 2 would be 20. So C9H20. So we're missing 8 hydrogens, and that corresponds to 4 pi bonds and or cycles. Now the structure of cumene is just isopropyl benzene. So let's see, does that make sense? We've got 1, 2, 3 pi bonds and 1 ring system. So there's 4. 4 is the index of hydrogen deficiency, and so that makes sense for this molecule. So let's have a look at that in more general terms, not just with hydrocarbons. If we have molecules that have halogen in them, then we need to adjust the formula because the halogen is taking the place of one of the hydrogens. So for example, if we go from CH3, CH2, CH3 to a molecule that is CH3, CH2, CH2 chlorine, we've deleted one of those hydrogens here and replaced it with a chlorine. So the reference formula for a monohalo hydrocarbon would have one less hydrogen than the hydrocarbon itself. And so the formula would be, for example, CnH2n plus 1 and then the halogen. We don't have to do any correction for molecules containing oxygen, sulfur, or selenium because they are divalent. So what do I mean by that? If we look at the structure of example once again, propane, and we replace that molecule, we put in an alcohol into that structure, we could have CH3, CH2, CH2OH. So now we've got an alcohol. We have replaced a CH3 group here with a CH2 group and a hydrogen, and we've just put this oxygen in between them. So overall, apart from the oxygen being introduced, we haven't changed the rest of the molecular formula at all. So the carbon and hydrogen part of those molecules will remain as CnH2n plus 2. Now, nitrogen and phosphorus are an interesting counterpoint to that. So if we look at the same reference hydrocarbon again, so let's look at propane, or just propane, and we convert that to CH3, CH2, CH2NH2, so that would be a simple amine derived from propane, so propylamine. In this case, we've got rid of one of these hydrogens, but we've replaced it with two hydrogens over here and added this nitrogen. So overall, we've gained a hydrogen versus the parent hydrocarbon. So plus 1H in going from propane to propylamine, from propane to propylamine. So therefore, our formula is going to be CnH2n plus 3 now. Instead of plus 2, we now have this extra hydrogen being added over here. So these are our reference molecular formulas we can use when we work out that index of hydrogen deficiency. And that becomes really important when we're looking at mass spectrometry, which allows us to work out the molecular mass and the molecular formula for a given compound. So what is mass spectrometry? Well, basically we take a molecule and we put it into an instrument that allows us to determine the mass of charged species that are going through the instrument. So we start off with the sample source. So this might be our molecule dissolved in some kind of solvent. We put it into something that creates ions from that source. So they're going to end up with positive or negative charges. We then put it into an accelerating plate here that makes it fly through a electron beam here, and we have a second accelerating plate here. Now we've got a beam of positive ions coming out of this ionization chamber here. So that beam of ions then goes through a magnet, and there's an interaction between magnetic fields and charged species so that they get their path changed by that magnet. And the degree by which their path is changed is related to their mass to charge ratio. So the most massive ions in the sample are deflected the least. So they end up going over here, whereas the lightest ions are deflected the most. So they end up going over here, and you can detect the differences between these ions with a collection screen over here. So it's really important that it's the mass to charge ratio that allows us to discriminate between different species. Now, in the simplest case, the charge is always going to be +1 for positive ions or -1 for negative ions. And it's normally much more common to do mass spectrometry with positively charged ions rather than negatively charged ions. So diagrammatically, we've taken a molecule, we've hit it with electrons, and then it might be a little bit counterintuitive, but those electrons have been high energy enough, they hit the molecule, and they eject an electron from the molecule. So now we have a molecular ion that has a positive charge and an unpaired electron. So we've just lost an electron from the species, so now there's an unpaired electron and a positive charge. So that high energy electron has gone in, and we end up actually ejecting 2 electrons at the end of the day. Now we don't really care about those, we're interested in the positively charged molecular ion. And so what we would expect is if we put in a molecule like this, so this is just 1, 2, 3, 4, 5, 6, it's just N-hexane. So it's going to be CnH2n plus 2, so that's going to be C6H14. That corresponds to a molecular weight or molecular mass of 86. So when we put N-hexane into the mass spectrometer, we see a peak at 86 for C6H14 with a positive charge and 1 unpaired electron. Now there's other masses here, and they correspond to this molecule breaking into fragments. So fragments within the mass spectrometer, and those fragments can tell us something about the structures of the molecule as well. Now, how does this help us? Well, that tells us the molecular mass for the compound that we're trying to analyze. So for example, N-hexane fits that formula CnH2n plus 2, whereas cyclohexane fits the formula CnH2n. So it should be 2 lower in its molecular mass. And indeed, when we put cyclohexane into the mass spectrometer, we get a peak at 84 rather than 86. Similarly, if we had a molecule with the structure of hexene, we would have a mass of 84 in that case as well. So we can get some information about the structure of these molecules. Now, the mass spectrometry tells us more than just the molecular mass, the species. If we do it with a high-powered instrument, we can get what are called high-resolution mass spectrums. And then that allows us to record the mass of our ions with a high degree of accuracy. So because now we're aiming for accuracy, we need to calibrate the instrument using standards, and we can actually record the mass of these down to 4, 5, or even 6 decimal places. And why that's important is that we can actually, in many cases, if we're looking at just the low resolution mass of the molecule, 88, a mass of 88 may correspond to a compound with C4H8O2, or it could correspond to a compound with C4H12N2, or a compound with C5H12O, or C3H8N2O. All of those molecular formulas correspond to a mass of 88. And really pretty close to each other in terms of the first 2 decimal places as well. However, if we accurately record the mass of these molecules, we can work out that what the molecular formula is, because the C4H8O2 has an accurate mass of 88.0524, whereas C4H12N2 has 88.1001, and so on. So each of these is diagnostic for the actual molecular formula for the compound, and so that can tell us what the molecular formula is. There's also a way that the isotopes of some elements can tell us something about what elements are present within the sample. So bromine is present in nature as 2 common isotopes, bromine 79 and bromine 81. And they're in roughly 1-to-1 ratio in natural abundance. And so in the mass spectrum of bromine-containing compounds, we'll see peaks that are 2 mass units apart. And one will correspond to a compound that has bromine 81 in it, and one will correspond to compounds with a bromine 79 within the structure. Okay, so that's all I'm going to say about mass spectrometry and how it can help us work out the molecular mass and the molecular formula for unknown compounds. Thanks for watching.